Good day, everyone. In the last video, I talked about the adiabatic approximation, and we looked at slow transitions versus fast transitions. And we said that if we have a Hamiltonian that is varying very slowly, then we could define these so-called instantaneous eigenstates, which are the solution of this equation. And this equation, I remind you, makes not very much sense. These instantaneous eigenstates are not eigenstates of any Schrodinger equation. They're not eigenstates of the time-dependent Schrodinger equation. And this thing here is not really a Schrodinger equation. It's just an equation that we can create at a particular time t and solve at a particular time t. And then we can have orthonormal solutions to that Hamiltonian at a particular time t. But because as soon as it starts evolving, the h itself changes, these are not solutions of the Schrodinger equation. The exact solution of the time-dependent Schrodinger equation I wrote using this capital psi, and we wrote this psi in terms of the instantaneous eigenstates in a way like this, where we had pulled out the dynamical phase term, we had the instantaneous time-dependent eigenstates, and this coefficient, which was time-dependent, I wrote as the Berry phase, but I didn't try and derive that for us. So what we'll do in this video is I'm going to derive the Berry's phase, and we're going to sort of motivate or justify the adiabatic approximation that says that transitions do not occur if ht is varying slowly enough. So let's get started. The first thing we're going to do is we're going to just substitute this ansatz for the actual wave function into the time-dependent Schrodinger equation that it has to satisfy. On the left-hand side of the time-dependent Schrodinger equation, we have I h bar d psi by dt, and that's going to be I h bar. And what I'm going to do is I'm going to differentiate each one of the terms inside the expansion. So we're going to have Cn dot, if I just differentiate the time-dependent coefficient, psi n, and I'm going to leave the phase factor, the dynamical phase factor, I'm going to put that one outside the brackets. So that's going to come along later. Plus I need to differentiate psi n itself. Plus I'm going to have to differentiate the phase factor itself. And so in this way, we've dealt with all three parts. When you differentiate this term, we get this one. We differentiate this one, we get this term. And when you differentiate this one, we get this term. Okay. That's all I need on the left-hand side. What about the right-hand side? On the right-hand side, I've got h psi. And that is applied to n Cn psi n e to the I theta n, which we should remember that Cn, psi n, and theta n are all time dependent, as is h. And then the h only applies to the sides. It doesn't. It has no effect on the coefficient Cn or the dynamical phase factor. So we can just go ahead and write that h of t psi n of t. And we can do that using the fact that these are the instantaneous eigenstates. So these are defined precisely by this equation. So we can write this as sum over n Cn e to the I theta n, and then when we apply h to psi, we're just going to get the instantaneous eigenvalue En of t times psi n of t. And then the last thing I'm going to need, oh, I forgot a dot up here. My apologies. That should have been the differential of the function. When you take the differential of e to the I theta, you need to take the derivative of theta down, not theta itself. So now we have theta n dot is equal to minus 1 over h bar ddt. Oh, and now I just see that I've made a mistake up in my previous definition. So I'll go ahead and fix that. That here, that should be a 1, not an I. So let me fix that. Minus 1 over h bar. As we're about to see, that will be the correct form. 0 to t, en of t prime to t prime. So we can take the derivative of this thing, and by the fundamental theorem of calculus, this is nothing but minus 1 over h bar en of t. So in the limit that the Hamiltonian is not varying, this will give us our usual phase factor of e to the minus I e t over h bar. So if theta dot is this constant, then theta will be that times time, and then e to the minus I e t over h bar, as expected. So this theta is sort of by construction to give the correct limit. I h bar sum over n. Let's just actually look at this third term. This third term here on the right hand side, this one here. That is sum over n of I theta dot cn psi n e to the I theta n. So I times I will be minus h bar. Minus 1 times h bar. I times I is minus 1. Then we're going to have sum over n of theta dot, which is now going to be minus en over h bar, which is time dependent. En is time dependent. Times cn psi n e to the I theta n. And that's equal to, so that minus 1 over h bar comes out. So we're just going to have sum over n of cn of t en time dependent. Just to remind us that all of these things are time varying quantities now. So we're going to have what's left. So this one matches exactly what's on the right hand side already, and so what we end up with is just the first two terms on the left hand side, which is I h bar sum over n of cn dot psi n plus cn psi n dot e to the I theta n equals 0. So far so good, and now what we do is we can multiply this on the left by some different function. So now we're going to take, which is still what we always do with perturbation theory. So now we multiply by some psi m. And what often you see in textbooks now is you'll multiply by psi n itself, but that skirts around the difficulties of the adiabatic method. So let's just do it properly, and m can be equal to n or not equal to m. Let's just see what happens. So the I h bar, of course, we can ignore now, and then we're going to then have sum over n of cn dot. Now remember, psi m and psi n are orthogonal to each other at all times, so we can just write this as delta mn plus, and the next term is going to be cn psi m psi n dot, that one's not necessarily orthogonal, e to the I theta n is equal to 0. Going one step further, then we can take the first term and we can apply the delta function operator and just pull out the one term on the from this sum, which is not 0 from this part. And so that's going to be Cm dot e to the I theta m equals minus sum over n of Cn psi m psi n dot. And that means that we can write this Cm dot as equal to minus sum over n of Cn psi m psi n dot e to the I theta n minus theta m. Right. Let me just now pull out one special term from the right-hand side, which is the term on the right-hand side. See, the term on the right-hand side, the sum on the right-hand side sums over all possible states, including m itself. So what we're going to do is take that one out because it's a bit special. It's special because we're going to have no dynamical phase factor for that one. And all the other terms are going to be represented here. We're not quite done yet because I want to express this psi m psi n dot in a slightly different way. So what I'm going to do now is a little bit of an aside. Imagine I start with the Hamiltonian h of t psi n of t equals en of t psi n of t. So start here with the equation which is for the instantaneous eigenstates. And I'm going to take the derivative in time of both sides. And a way to think about this is sort of like at every point in time t, I have a Hamiltonian and I have a solution for every single point in time. And so for each one of these quantities, I can define a parameterized function of t. And I can define a derivative with respect to that time, which would be like psi at t plus delta t minus psi at t over delta t, in the normal way that you define a derivative. And so when I say I want to take the derivative of this thing, that's still a well-defined quantity. So I want to take the derivative of this equation, and I get and now I multiply it by m, psi m as a bra, and integrate. And I realize now that I should have put hats everywhere. Now I'm going to apply the h to the left here and pull out a factor of em. Now remember what I was trying to do. I was trying to simplify this term up here for n not equal to m. So now I'm going to take that n not equal to m and now I can express the overlap function here in terms of this h dot matrix element. And now comes the adiabatic approximation. So far this is exact. And the adiabatic approximation is just forget about the second term. It's smaller than the first term. Now, that's quite difficult to prove rigorously, but what I'm going to do at the end of this video is I'm going to come back to that, and I'm going to justify it in a different way. Justify the fact that there are no transitions. So what we would do here is, firstly, this thing is not zero. It isn't zero, right? The adiabatic approximation says it's close to zero, and it gets more close to zero the slower h dot is. So h dot is small. That means that this matrix element gets very small, and this is small compared to this one. And the slower it is, the closer this is to zero. So the question is not, is this zero? It's not zero, right? We know that. But what the question is how wrong are we when we say that? What's the error in the assumption that this thing is zero? So we're going to come back to that subtle point. So we can only make this approximation if h dot mn, which is the matrix element of h dot, is very, very small. So if we have a very slow process, then this second term is going to be very small. In that case, we can write Cm dot is approximately equal to minus Cm psi m dot. And this is an equation for the coefficient Cm that will solve the time-dependent Schrodinger equation. So in other words, if we have a Cm which solves this equation, then when we substitute it back into our full equation for psi, then we will satisfy the time-dependent Schrodinger equation to a certain level of accuracy. What is the solution of this? Well, we showed it last time. It's Cm is equal to Cm naught e to the I gamma m, where gamma m was the real Berry's phase. So we put this factor of I, we don't need this factor of I, but we put it in here and we put another one here. And so that gives us this minus sign in the differential. And we do that because in this way, this gamma, this whole thing is a real quantity. This part's imaginary, this part's real. So this is indeed a phase factor. Okay, so the big thing that we have to kind of come back to is how are we saying that there are no transitions? What's the evidence for there not to be any transitions here? How do we prove that? I want you to imagine a time-varying Hamiltonian, as we did before. It's doing something like this. And imagine that at some particular time, and I'm just for convenience sake, we'll call it t0, some t0, and we're going to just take the wave functions at that time t0 and use those in our solution to get to the next little time period, which is going to be a little epsilon later. We're going to use the time-dependent perturbation theory, and we're going to do it in the basis of the original time t0. Remember, in perturbation theory, what we do is we integrate our equations, the time-dependent Schrodinger equation, in terms of the original basis functions. We never change the basis functions. We don't define these instantaneous eigenstates. And what we're going to do is assume that we've gotten up to the point t0 without having a transition so far. And what we're going to do is we're going to see what's the probability of having that transition over the next little period epsilon. And if that is very small, then we can say, well, we're going to make it to T naught plus epsilon. And by chaining all of those together, we'll make it to the very ends of our adiabatic transition. So we have this assumption that Cn at time T naught is equal to 1, and all the other CMs are equal to 0. And then what we want to know is the transition rate Cm at time T naught plus epsilon. So because this is only acting for a very short time and it's a very small perturbation, we can just use time-dependent perturbation theory. So the time-dependent perturbation theory expression is Cm first order is the sum over all of the states minus I over h bar Cn naught. This is me just writing out the expression for the first order time-dependent perturbation theory. So that's our expression. And now I'm going to just write it in our case. So in our case, what we have is we only pick out the one term. So you have minus I over h bar, Cn naught equals 1. And now we would go from T naught to T naught plus epsilon of our expression HMN, which is the time-dependent Hamiltonian. And I should have written here, this is H. Time-dependent Hamiltonian, and e to the I omega m n t dt. And I remind you that this is taken when m and n are at time t naught. So omega m n equals e m at time t naught minus en at time t naught, obviously with the h bar there. Okay, to make things slightly easier, we're just going to let t naught equals 0. That's just, you can set it to whatever you like. It's just a little shift, but this makes things slightly easier. And so we can solve this integral. Even though we don't know much about it, I do know that I'm just making a very small perturbation with h, and I'm assuming that's kind of linear in the range of t naught to t naught plus epsilon. So I'm assuming that this is just a little linear bit. If we want to include higher order terms, we can do so, but let's just see what happens if we just include a linear term. And now what I'm going to do is I'm going to integrate by parts. So minus I over h bar, and I'm going to integrate by parts. So I'm going to take the derivative of the HMN term, and I'm going to integrate the e to the I omega t term. So that will give me the first term, and I integrate this one, e to the I m n t over I omega m n. So when I differentiate it, it gives me my original function from naught to epsilon. Remember, t naught equals naught. And now you can see why it just makes it a little bit easier to write. And minus becomes plus I over h bar, the integral from naught to epsilon, h m n dot e to the I omega m n t over I omega m n dt. And now what we need to do is we need to expand out our HMN. And so what we can do with this is we can because we're assuming, so take this 1 over I omega outside, so this would be minus 1 over H bar omega mn, and I'm going to expand out this H into H mn at time t equals 0 plus a derivative. I'm going to keep one derivative term at time t equals 0 times t, and I'm going to also expand the exponential function 1 plus I omega mn t. So again, because this epsilon is a small number, I can just expand both of these terms to first order. The whole expression is only going to be valid to first order. We're not going to get more accuracy than that somehow, right? And second term here, I cancel out the i's, so I got 1 over H bar omega mn, and now I have an integral. The HMN dot I'm also assuming is a constant. If we look at this picture of H, we can see that's constant over the range of interest. So I'm going to take this outside as well, and obviously evaluated anywhere, but particularly at time 0, times the integral from, I can just do that integral now. Actually, no, enough. So it's either I omega t, so I have to integrate that, and so I have to integrate e to the I omega mn t over I omega mn from 0 to t. So I've brought down another factor of 1 over I omega because this is the integral of just the numerator here. I've taken this one outside, and now I'm just integrating this one, so I bring another factor of I omega down. And I will expand that again. So we will only keep terms up to order epsilon. So we'll go minus 1 over H bar omega. And now we can see that we've got mn epsilon plus H dot mn naught epsilon. So write it like this. And the second term is going to be, and then there's going to be the cross term, which is t squared. So we ignore the t squared, right? And now we're going to have, for this one, I'll do the same trick. So we've got H dot mn at 0 over H bar omega mn. And that's going to expand the exponential as 1 plus I omega t. So the 1 is going to go away. So we're just going to have, I'll just write it, 1 plus I omega mn t. Right, we're just keeping that first term in the expansion. There should be an epsilon up here. And the next thing is to note that this HMN at time t equals 0 is 0 because we chose those instantaneous eigenfunctions at time t equals 0, that means that the matrix element at time t equals 0 is 0, right? They're orthogonal by definition. So that first term goes away because of our choice. And then we can see that we're going to just have minus H dot mn times epsilon plus times epsilon. And so we're going to get 0. And of course, what I'm saying is not that it's 0, but it means that it's higher order. It's order epsilon squared. So there may be some terms that are size epsilon squared, but what we've shown is that there are no terms of size epsilon. In other words, for a very short period of time here, a short period of time epsilon, the rate of change of Cm is going as epsilon squared, right? And that's why all the way back here we can ignore this transition term. That transition term is one order at least smaller than this term. This term is changing as epsilon itself, right? It's the first derivative in time. This one here is the derivative in time squared at least. And you can keep higher order terms in the perturbation theory to see what happens at the next order in epsilon squared. And the point is that, look, indeed, this is definitely not zero, but it's close to zero. And if you go slow enough, then at any particular time, you have such a small probability of transition that you can just keep doing this again and again and again. So the rate of transitions is one order in smallness parameter slower than the evolution of the wave function of the instantaneous eigenvalues. And that's basically a proof, or at least an indication, of why the adiabatic process works. Thanks for your time.